Hey everybody, welcome back. Mr. Smith here. Today's topic is about mass defect and binding energy in the nucleus. Boy, does that sound dull. No, not at all. It's crazy amazing. When we talk about mass defect in the nucleus, we are not talking about a situation where people, don't know what they're doing or they're being destructive, like actually a lot of YouTube guys are when they do stuff like throw sodium in water. In fact, here we have a YouTuber named Nick Uhas. I want to give him a shout out because he's actually pretty careful about how he does it. But if you haven't seen this chemical reaction, it's a pretty fun chemical reaction. So check it out. So when we talk about mass defect, it's not that we're talking about grown men with credit cards acting like 15-year-olds. What we're talking about is a violation of something we hold near and dear, something really important. So this should be one of the greatest hits of your high school science career. The idea that mass is conserved. When did you learn that? I don't know. I hope you remember Antoine Lavoisier, one of the granddaddies of chemistry. He did elaborate experiments in the late 1700s where he did reactions and showed that if you counted up the mass of all the reactants on this side, it always added up to the mass of the products on that side. So if you're reacting sodium and water, you take the mass of the sodium, the mass of the water, you get sodium hydroxide and hydrogen, you capture all that stuff, all this stuff, the mass always works out, right? Wrong. It turns out that mass conservation is not actually true. Lavoisier's balances weren't sensitive enough to really see what's actually going on. What happened? Well, in the middle of it, Albert Einstein in 1905 published probably the most famous formula in the history of physics, E equals mc squared. Here's one of the things it really means. That in every reaction that generates energy, a little bit of mass is actually deleted from the universe. We're talking about just X'd out, gone, forget it. Also, I guess that means that conservation of energy is out the window. Right, it is. They're both out the window. And with 1905's formula, what Einstein did was to recast all of the physics of energy that came before into now a formula that's called the conservation of mass/energy. So let's go historically back to where it all began. So we talked about the experiment where in 1932, Cockcroft and Walton, these guys that are flanking their mentor Ernest Rutherford, in the Cavendish laboratory did this experiment. They took an atom smashing machine like the ones we'd studied, they smashed protons into lithium, and they got helium. Well, if you look at the parts that are going on here and you add up the mass numbers, it looks like they should be equal, right? We've got a proton that has a mass of 1, lithium has a mass of 7, these heliums all have a mass of 4, and I've got 2 of them. So it seems like I've got 8 mass units on this side and 8 mass units on this side. Well, here's the catch. It turns out that now, in the 20th century, people had enough significant digits that they could actually measure missing mass. And where does it really present itself? In nuclear reactions. Because in nuclear reactions, the forces and the energies involved are insanely big. Here's the example. What we're going to do first is take a look at this table of masses that's super handy from our textbook. We've got the masses in kilograms of an actual proton, an actual neutron, actual electron. Then we've got the masses of these things in atomic mass units. And I want you to notice that the mass of the proton and the neutron, neither of them is exactly equal to 1. An electron, still super tiny. So what are we going to do here? Let's just go lay out the numbers and see what we see. The mass of one proton. Okay, got it. We can write that down. 1.007276 AMUs. So we throw one of those at a lithium-7 atom. Well, we talked about that guy before in our first slide deck, 7.016004 AMUs. And what do we get? We get 2 of these helium-4s. So there's an appendix in the back of our book called Appendix B. It is super helpful. You'll look up the masses of all sorts of things there. So 4.00603 is the actual mass of a helium-4. And so this side ought to equal that side, right? No, it doesn't. So what you get when you get this side is 8.023 and you could get some more if you want, 8 AMUs. So that's how much mass we have on this side. Does that yield to this side? 8.005205. It doesn't. What happens? An actual measurable mass in the universe just got wiped off the books. And that's where the energy comes from. It comes from the fact that the matter actually went missing. So let's go and take a look how this applies to real nuclei. In this example, what we're going to do is to take a look at iron, which is the most stable nucleus of all the nuclei on the periodic table, for reasons we'll talk about. And what we're going to do is a simple game. We're going to play God, and we're going to build iron out of spare parts. So just imagine this is like a Lego enterprise, and we're just going to grab a bunch of protons, neutrons, and electrons and add them all together. Okay, so that's the first task. So first thing we need to do is what's inside of an iron 56. Well, you can look it up on the periodic table. Iron has an atomic number of 26 and a mass of 56. And so what that means is our list of raw materials is going to include 26 protons. So what I'm going to do is just get the mass of 26 protons. So 26 times 1.007276. 76 atomic mass units. All right, and we'll get those. So what's the mass of all the protons inside of an iron is 26. You notice we're keeping a lot of decimals. You do have to keep a lot of decimals as you do this game. So 189176. We can always round off at the end, but when the game is that thing significant or did it make a difference, you really want to keep it close. So also in iron, if it's uncharged, we have 26 electrons. So 26 of these little guys, 0.000, let's see, 548 of an atomic mass unit. And all the mass of all the electrons adds up to not very much. So 0.014263 atomic mass units. Okay, and then finally, how many neutrons do we have in an iron 56? 30 of them, right? So 56 minus 26 gives us 30 of the neutrons. So that's 1.008665 atomic mass units. And you go and do all that. All right, so you add all that stuff up and you get 30.25995. Okay, so this is a task that's easy. What you're going to do when you do these problems is use this chart. And you're going to do exactly what I did, get the mass of all the constituent parts. It looks like it adds up to around 56, right? Well, let's go get them. So it adds up to 56.46339 atomic mass units. There you go, the mass of an iron 56, right? No, it's not. Appendix B is an appendix in the back of our book. And I'll give you the table or I'll give you these numbers. But what you do is you look up the actual mass in the real world of an iron 56. And it turns out it's lighter. And it's significantly lighter. So if I were to take this 56 and subtract the 55.93, etc., what I actually get is the mass defect. And that's what we're going to do in the very next slide. So let's go get it. So here we go. You take the mass of all the parts, subtract the actual mass, and you get the mass defect. What does it mean? The mass defect is missing mass that turns directly into the huge amount of energy that it takes to hold this nucleus full of protons that hate each other in the ridiculously small space that's the nucleus. So what we're going to do is show you how that directly turns into energy called the binding energy of the nucleus. It's actually a couple of really easy calculations, and we're out for this slide deck. So we're going to take the missing mass, 28448 atomic mass units, and we're going to convert that into kilograms. Well, we've done that before. We've got 1.66 or so times 10 to the negative 27 kilograms in one of these atomic mass units. And when we do the math, we go and find out that there's 8.775, I believe, times 10 to the negative 28 kilograms that have gone missing. It sounds really small, right? Well, it kind of is, except the binding energy is given by E equals mc squared. So we pull it all together right here. So even a pretty small amount of missing matter gets multiplied by a big number, and it turned out to be significant. So let's go get it. We've got 8.775 times 10 to the negative 28 kilograms times the speed of light, so 2.997 times 10 to the 8 meters per second, and it doesn't get any smaller when you square it. So you do all the math, and what do you get? 7.8 times 10 to the negative 11 joules. Well, that sounds really small, except again, this is the amount of energy that's associated with one atom per mole. This is billions of times more energy than you get by exploding sodium. Billions, 10 to the 9. Huge, huge, ridiculous quantities of energy associated with the nucleus. And so going back to 1932, people knew there had to be huge energy associated with the nuclei of atoms because the nucleus is just so improbable. Okay, so let's wrap it up. What we're going to do is do a quick conversion, and we're going to turn this into MeVs. So remember, MeVs is 1,000,000 electron volts. So we're just going to take and use a conversion that you can copy in the future, and we can talk about it in class. Hopefully you remember it, but if not, don't sweat it. So 1 MeV is the same thing as 1.6 times 10 to the negative 13 joules, and that had to do with the charge of an electron, if you remember. So what that turns out to be is 492 and change, 493 almost MeVs of energy associated with the nucleus. Last thing we're going to do is the thing that they do in the textbook. When you compare atoms to other atoms, like iron versus uranium, iron turns out to be super stable, and here's why. The amount of energy in MeV per nucleon is a measurement of how stable the nucleus is. So what we're going to do is take that 493 or so MeVs and divide it by the 56 nucleons that are inside of the iron. And for the reasons that we'll get into about what makes nuclei work, this turns out to be the biggest number of any of the nuclei on the periodic table. So iron is the ultimate kingpin of stability. Who knew? Well, now you do. All right, so bring your questions. We've got a lot to talk about. Have a great day and see you soon. Bye-bye.